Imagine a day unlike any other. It does not begin with a flash of light or the roar of an explosion. There is no warning from the heavens, no tremor from the deep. It starts with a whisper, a physical impossibility that begins perhaps in the deepest trench of the Pacific Ocean. A single subatomic particle, smaller than any virus, heavier than a mountain, arrives from the cosmic dark. It is an infinitesimal seed of something new. This is not a collision, it is a conversion. The first water molecule it touches is not annihilated. It is transformed, its fundamental nature rewritten in an instant. The atoms of hydrogen and oxygen, so familiar to us, find their constituent quarks rearranged into a new, unthinkably stable and dense configuration. This one converted molecule now shares the same alien property. It touches its neighbor, and the process repeats. A chain reaction begins, not of fire, but of crystalline change. This is a contagion spreading at the speed of chemistry, a silent, inexorable plague upon matter itself. On the surface, for a few fleeting moments, nothing appears wrong, but then a strange stillness settles over the ocean. The waves, those timeless engines of planetary rhythm, begin to slow, their crests thickening, losing their energy. The water is not freezing into ice, it is congealing, becoming something harder than diamond, denser than lead. A creeping solidity spreads outwards from a single point, a wave of pure transformation perfectly silent. Sea life caught in its path is not killed, it is subsumed. Every cell, every strand of DNA, every complex protein is disassembled at the quark level and reforged. The vibrant, chaotic biology of the ocean floor becomes a single, monolithic statue of exotic matter. The wave of change reaches the shorelines. The white sands of a tropical beach, each grain a universe of history, are touched and converted, becoming part of the growing mass. The living coral reefs, those kaleidoscopic cities of life, are overwritten, their intricate beauty erased, and replaced by the monotonous perfection of this new substance. From space, our beautiful blue marble begins to look diseased. A dark, unnatural sheen spreads across the Pacific, a patch of ocean that no longer reflects the sun in the same way. It is a cosmic cataract growing over the eye of the world. The process accelerates. The solidifying crust of strange matter now contacts the continents. Rock, soil, and life are all just configurations of atoms, and no configuration is safe. Forests of ancient redwoods, bustling cities humming with electricity, the great ice sheets of Antarctica, all of it is just fuel. The transformation burrows deep into the planet's crust and mantle a relentless journey towards the iron core. As more and more of Earth's mass is converted, the planet itself begins to physically shrink. Its gravity intensifies catastrophically. The atmosphere, once a gentle blanket of air, is crushed downwards, liquefying and then solidifying onto the contracting surface. The moon, our constant companion, is pulled from its gentle orbit, spiraling inwards towards a world that is no longer its mother. In its final moments, the Earth is a sphere of hyperdense matter, no larger than a city but containing the mass of a planet. It is a featureless, perfectly smooth orb of what physicists call strange matter, a cosmic tombstone where a world once lived. This is not an apocalypse of fire and fury. It is a quiet, orderly, and absolute apocalypse of physics. And the theoretical agent of this planetary extinction is the Strangelet. This chilling vision, this ultimate cosmic nightmare, is not born from the pages of science fiction. It emerges from the very heart of our most advanced understanding of the universe, from the arcane world of quantum chromodynamics. It is a ghost lurking within the standard model of particle physics, a dark possibility hidden in the mathematics that describe our reality. The story forces us to confront the most fundamental of questions. What is the ground beneath your feet truly made of? What are you made of? We believe we inhabit a solid, reliable reality, a universe built on dependable rules and stable materials. But what if the entire cosmos we know, every star, every planet, every living being, is fundamentally unstable? What if we are all living in a false state, a cosmic illusion, and the true ultimate state of matter is something else entirely? Something alien, something dense, something strange. Is this Strangelet a phantom, a mere theoretical curiosity destined to remain forever confined to blackboards and supercomputers? Or is it a genuine physical threat, a silent hunter drifting through the cosmic void, an existential risk? Profound, it redefines our concept of catastrophe. To even begin to understand the danger, we must travel inwards. We must undertake a journey to a realm far smaller than atoms, beyond the familiar world of protons and neutrons. We must enter the subatomic kingdom of the quarks. For centuries we believed the atom was the final indivisible unit. The very name, times atomos times, meant uncuttable in ancient Greek. Then we shattered that illusion. We discovered it was a miniature solar system, a dense nucleus orbited by a cloud of fleeting energetic electrons. But the journey did not end there. Physicists, driven by an insatiable curiosity, aimed their most powerful instruments at the nucleus itself. They saw that it too was a composite object, a tightly bound cluster of two types of particles, the positive protons and the neutral neutrons. For a time, this seemed to be the bedrock of reality. Protons, neutrons, electrons, these three particles could build every element in the periodic table, from the lightest hydrogen to the heaviest uranium. They were the holy trinity of matter, the building blocks of everything, but even this picture was incomplete. When we began smashing these particles together in vast circular accelerators, burying them miles underground, we made a discovery as profound as any in human history. The protons and neutrons were not fundamental, they were containers. Inside each one were even smaller, even more elemental particles. The physicist Murray Gell-Mann, with a characteristic flair for the whimsical, named them quarks, borrowing the term from a line in James Joyce's enigmatic novel, Times Finnegan's Wake times 3 quarks for muster mark. The theory was stunning in its elegance. All the matter that makes up our world, our bodies, our sun, is composed of just two primary types of these quarks. We call them the up quark and the down quark. A proton is a tiny sac holding two up quarks and one down quark. A neutron, its near twin, holds one up quark and two down quarks. That's it. That is the fundamental recipe for the visible universe. An alphabet with just two letters that through endless combination spells out everything from a grain of sand to a spiral galaxy. This arrangement is incredibly stable. The forces binding these quarks together, the strong nuclear force, is the most powerful force we have ever discovered in nature. It acts like an unbreakable cosmic glue, ensuring that protons and neutrons remain intact for trillions of years, providing the reliable scaffolding upon which reality is constructed. The stability of your own body is a testament to this incredible power. But the universe, it turns out, is more creative than we imagined. As our particle accelerators grew more powerful, we began to glimpse a hidden world, a shadow family of particles. It was as if we had been listening to a symphony in only two notes, and suddenly we discovered there was a whole orchestra of other sounds. We found there were not just two flavors of quarks, there are 6. Alongside the familiar up and down, there was the charm quark and the strange quark, followed by the even more massive top quark and bottom quark. These other 4 quarks are ghosts. They are visitors from a higher energy state of the early universe. In our cooler modern cosmos, they are incredibly unstable. We can forge them in the fury of our colliders, but they exist for only the most infinitesimal fractions of a second before decaying back into the lighter, more stable up and down quarks. They are mere flickers on a screen, ephemeral sparks of a more violent time. For decades, that's all they were, fascinating but transient. They were footnotes in the cosmic story, not main characters. The strange quark in particular was true to its name. It was heavier than the up and down quarks, possessing properties that seemed peculiar to the physicists who first detected its tracks. But like its exotic brethren, it was a fleeting thing, a mayfly in the world of particles, born and dying in less than a nanosecond. And so our reality seemed safe, guaranteed by this decay. The universe we know is an up and down quark universe. The strange and other exotic quarks were just temporary guests, but then in the late 1970 seconds and early 1980 seconds, a deeply unsettling new idea began to take shape. It was a hypothesis that emerged not from an experiment, but from the raw predictive power of pure theory. It started with a simple, almost naive question. What if you could assemble a large collection of quarks, not just in triplets like protons and neutrons, but in a vast teeming sea of thousands, millions or more? And what if in that sea you included not just up and down quarks, but a roughly equal number of strange quarks as well? The mathematics began to suggest something extraordinary. According to the rules of quantum chromodynamics, such a mixture, a soup of up, down and strange quarks, might not be unstable at all. In fact, under the right conditions, this bizarre amalgam could be the single most stable configuration of matter possible in the entire universe. This is the strange matter hypothesis, and its implications are staggering. It suggests that the very protons and neutrons that form our bodies and our world are not the ultimate ground state of existence. They are instead what physicists call metastable. Think of a ball resting in a small dip on the side of a very tall mountain. The ball is stable enough. A gentle breeze won't move it. It seems perfectly secure. But its position is not truly permanent. Far below lies a deep, wide valley, a state of much lower, much more profound energy and stability. All it would take is one significant push to send that ball rolling down the mountainside to its true and final resting place in the valley below, releasing a tremendous amount of energy on the way. The strange matter hypothesis proposes that all of our ordinary matter, the matter of you and me and the stars, is that ball on the mountainside and the valley below. That is the state of strange matter. We live in a fragile, temporary state, a universe built on a cosmic lie, waiting for the right push to collapse into its true form. And the push, the catalyst that could start the fall, that would be the strangelet. A strangelet is a hypothetical microscopic nugget of this strange matter. It could be as small as a nucleus or as large as an asteroid, but its properties would be unlike anything else in nature. It is not radioactive in the conventional sense. It does not decay. According to the hypothesis, it is the most stable thing that can exist. Its danger comes from a far more insidious property. It is catalytic. It is the seed crystal in a supercooled liquid, the spark in a powder keg. In Kurt Vonnegut's novel Times, Cat's Cradle Times, he imagined a substance called Times Ice 9 times, a fictional form of water that was solid at room temperature. A single crystal of Times Ice 9 times dropped into a river could by touch alone rearrange all the normal water molecules into its own stable solid form, freezing the world's oceans. A strangelet is the real-world physicist's version of Times Ice 9 *. If a strangelet were to make contact with an atomic nucleus, the intense pressure and the fundamental laws of physics would create an irresistible temptation for the quarks inside. The up and down quarks in the nucleus would be persuaded through the strong nuclear force to flip their identity, rearranging themselves alongside the quarks of the strangelet into the more energetically favourable up-down strange configuration. In this process, the original nucleus ceases to be. It is absorbed, assimilated into the strangelet, making it slightly larger, and in this conversion a burst of energy is released. The newly expanded strangelet now has a larger surface area ready to contact and convert the next nucleus it encounters. The process would be relentless, unstoppable, a chain reaction that feeds on ordinary matter, transforming it atom by atom into more strange matter. It wouldn't burn matter or blast it apart. It would simply eat it. It would rewrite the source code of reality one nucleus at a time. This is a terrifyingly efficient mechanism for destruction. A single strangelet possessing a net positive electric charge would be drawn to the negative electron clouds of atoms, effortlessly burrowing its way to the nucleus. Once there, the conversion would begin, a silent contagion spreading through any material it touched, leaving behind only a growing mass of ultra-dense, inert, strange matter. The very ground we stand on could become the fuel for its growth. The air we breathe, the water we drink, all of it vulnerable. This leads us to the critical questions at the heart of our journey. Could such objects truly exist? Is strange matter just a mathematical curiosity, or has the universe actually manufactured it somewhere in the cosmic darkness? To find the answers, we cannot stay on Earth. We must look outwards to the most extreme and violent environments the cosmos has to offer. We must journey to the graveyards of giant stars to the unimaginable pressures inside celestial objects known as neutron stars. These are the cosmic laboratories where matter is crushed to densities so extreme that our earthly physics begins to break down. It is there in those stellar cores that strange quarks might not be fleeting ghosts, but could be liberated to form entire oceans or even entire stars made of strange matter. And if such objects exist, could they collide? Could they spray the galaxy with droplets of this cosmic poison, launching strangelets on interstellar journeys that could one day intersect with a small blue world in the suburbs of the Milky Way? And there is another more unsettling question. Do we have to wait for the universe to send one to us? Or could we, in our relentless quest for knowledge, unwittingly create one right here at home? Our most powerful particle accelerators, like the Large Hadron Collider, are designed to recreate the energy levels of the early universe. In our search for the secrets of creation, could we accidentally stumble upon the recipe for our own annihilation? Could we forge a microscopic strangelet that, once born, could begin the silent, unstoppable consumption of our entire planet? Scientists who operate these machines are confident the risk is zero. But the question lingers, a shadow cast by our own ambition. We are caught between a profound intellectual curiosity and a terrifying, if remote, existential possibility. The Strangelet represents the ultimate double-edged sword of physics, a concept of incredible theoretical beauty that also happens to describe the perfect weapon for planetary destruction. Our investigation begins now. We will sift through the evidence separating scientific fact from speculation. We will travel to the bleeding edge of astrophysics and particle physics, speaking to the researchers who live and breathe these questions. We will explore the cosmic cauldrons where strange matter might be born, and we will descend into the subterranean rings where we attempt to mimic the birth of the universe. The story of the Strangelet is the story of our search for the ultimate nature of reality, a search that forces us to confront the possibility that the universe is a far stranger and perhaps more dangerous place than we have ever dared to imagine. What if the very chair you are sitting on the ground beneath your feet, the solid, dependable reality you take for granted, is all a cosmic accident, a temporary arrangement, a placeholder for something far more stable and far more strange? It's a thought so profoundly unsettling it borders on forbidden, challenging the very nature of existence itself. We live our lives cushioned by an illusion of permanence. We trust that a rock will remain a rock, that the elements forged in the hearts of stars are the final, definitive answer to the question of matter. But the universe, in its infinite and often terrifying imagination, may have a different final chapter written for everything we see, everything we touch, everything we are. To understand this chilling possibility, we cannot look to the stars. Not at first. Our journey must begin by traveling in the opposite direction. We must plunge inward, shrinking down past the scale of human perception, past the microscopic, into a realm governed by forces so powerful and alien they make the gravitational pull of a black hole seem gentle, down into the heart of a single atom. Here, in this subatomic dominion, the familiar rules of our world evaporate. We bypass the frantic dance of the electron cloud, a ghostly sphere of probability, and arrive at the nucleus, an object of impossible density. Almost the entire mass of the atom is locked away in this infinitesimally small kernel, a fortress built from two fundamental particles, the proton and the neutron. For much of the 20th century, we believed this was the end of the line. These two particles, the stalwart keepers of cosmic identity, were thought to be the final indivisible building blocks. A proton gives an atom its charge, its very name in the periodic table. Along with the neutron, it dictates its weight, its stability. Together they are the architects of the ordinary. They build hydrogen, the fuel of stars. They construct oxygen, the air we breathe. They assemble carbon, the scaffold of life itself. Everything you have ever known is a symphony composed from these two simple notes. But what if the architects themselves are built from something smaller? What if the fortress of the nucleus has a secret hidden blueprint? Driven by this relentless curiosity, we built machines of unimaginable power, cathedrals of science, miles in circumference. particle accelerators designed to do one thing with brutal elegance: to take these fundamental particles, accelerate them to nearly the speed of light, and smash them together, hoping to crack them open and glimpse the secrets held within. What we found inside rewrote the story of the cosmos. The proton and the neutron were not fundamental at all. They were composite particles, each a tiny vessel containing an even more elementary trinity. We had discovered quarks. The components of the proton and neutron are of two flavors, as physicists call them: the up quark and the down quark. They are the letters in a cosmic alphabet of almost divine simplicity. A proton is two ups and a down, a neutron two downs and an up. With just these two particles bound together by a force of incomprehensible strength, the strong nuclear force, you can construct the nucleus of every single element in the universe. Every star, every planet, every living thing, all meticulously scripted from an alphabet with only two letters. This force that binds them is nothing like the gravity or electromagnetism of our daily lives. It is a cosmic superglue. The more you try to pull two quarks apart, the stronger the force between them becomes, as if they were connected by an unbreakable elastic band. Energy pours into the band until it snaps, but it doesn't release the quarks. Instead, the immense energy of the snap condenses following Einstein's famous equation and creates a brand new quark and antiquark out of the vacuum itself. The original quark is never left alone. It simply finds a new partner. Quarks are the ultimate social particles condemned to exist only in groups. They are never ever seen in isolation. This elegant, tightly bound system of up and down quarks is the foundation of our reality. It is stable, it is predictable. It is, for all intents and purposes, times us asterisk. For a time it seemed we had finally read the universe's source code, but physics is a discipline haunted by anomalies, by tiny imperfections in our theories that when pulled can unravel everything we thought we knew. The ghost in this machine emerged from the violent debris of our particle collisions. Among the familiar fragments, physicists began to see new particles, exotic and unruly strangers that didn't fit the simple two-quark model. They were heavier and more perplexing. They had a property of strangeness. This wasn't just a whimsical name, it was a genuine scientific puzzle. These strange particles were being created through the strong nuclear force, which meant they should have decayed incredibly quickly in a mere fraction of a second. Yet they persisted, living for lifetimes that were on a nuclear scale eons longer than expected. They were behaving strangely. It was as if a firework designed to explode in a flash instead decided to hang in the air, glowing placidly for minutes on end. There had to be a missing piece of the puzzle, a hidden rule they were following. The solution was as elegant as it was profound. The cosmic alphabet wasn't made of two letters. There was a third, a heavier, more exotic cousin to the up and down quark, the strange quark. When this new quark was produced in a collision, it couldn't decay via the powerful, strong force. It was forced to use a much slower, more cumbersome interaction called the weak force. This explained its strangely long life. The discovery opened up a whole new family of particles. The particle zoo, as it became known, was suddenly filled with an array of exotic beasts, all containing this new, strange ingredient. And yet in the world outside our accelerators, this quark remained a ghost. Its extra mass makes it inherently unstable. Left to its own devices, a strange quark will rapidly decay in about 1/10 of a billionth of a second, transforming into the lighter, more familiar up quark. It is a fleeting visitor, a momentary ripple in the fabric of reality before it settles back into the mundane. This is why we are not made of it. The universe, it seems, prefers the lowest energy state, the path of least resistance, and the lightweight, stable combination of up and down quarks appeared to be the ultimate ground floor of existence. Our matter was safe. Our reality was secure. The story should have ended there, but in 1984, a physicist named Edward Witten, a mind of once-in-a-generation brilliance, asked a question. A question so simple, so dangerous, it threatened to undermine the very bedrock of stability upon which our entire cosmos is built. He considered the extreme environments of the universe, places where matter is crushed beyond all recognition like the unfathomable core of a neutron star. In such a place, protons and neutrons are squeezed so tightly together that they dissolve into a vast, undifferentiated sea of their constituent up and down quarks. Imagine a room packed to the ceiling with people, all of them standing. This is our sea of quarks. Now, physics has a fundamental rule for particles like quarks, the Pauli exclusion principle. It states that no two identical quarks can occupy the same quantum state. They each need their own space, their own energy level. As you cram more and more up and down quarks into this cosmic room, they are forced into higher and higher energy states. The room becomes energetically expensive, unstable, and ready to burst. Witten's question was this: what if you could open a door and let a new type times of person into the room? What if you could introduce strange quarks into this hyperdense soup? Because the strange quark is a different particle. The Pauli principle doesn't restrict it in the same way. It can fill the low energy states that were already taken by the up and down quarks. Suddenly, a new pathway opens up. By converting some of the high energy down quarks into strange quarks, the overall energy of the entire system could dramatically decrease. The initial cost of creating the heavier strange quark would be more than repaid by the enormous energy savings from relieving the pressure. This leads to the hypothesis, the single most terrifying idea in particle physics, the strange matter hypothesis. It posits that a near equal mixture of up, down, and strange quarks, a substance called strange matter, is not just a theoretical curiosity. It might be the true ultimate ground state of all matter in the universe, more stable even than the protons and neutrons that make up you and me. This idea turns our understanding of the universe on its head. It suggests that all the ordinary matter we see, the stuff of galaxies, stars, and life, is in a metastable state. Think of a ball resting in a small dip on the side of a great mountain. It's stable for now. It will stay there as long as nothing disturbs it. But it is not in the lowest possible energy state. The true state of rest, the deep valley floor, lies far below. In this analogy, our universe of protons and neutrons is that ball on the mountainside, and strange matter is the valley floor. All that is needed to start an unstoppable cataclysmic cascade is for a single piece of this truly stable matter to touch our metastable matter, a single seed. A fragment of strange matter, colloquially known as a strangelet, would be the most perfect predator in the cosmos. It would not need to be large. A microscopic lump would suffice. If such a strangelet were to encounter an atomic nucleus, it would begin a chain reaction. The strong nuclear force would pull the nucleus apart, and the strangelet would absorb its quarks, converting them one by one. The up and down quarks of the ordinary nucleus would find it energetically favorable to transform into a blend of up, down, and strange. In the process, the strangelet would grow, releasing a burst of energy. The newly enlarged strangelet would then encounter another nucleus and another. The conversion would spread like a firestorm through matter. An infection for which there is no cure, no firewall. It is a process of conversion, not annihilation. The Earth would not explode. It would simply be transformed from the ground up into a new form of existence, a silent, dense, featureless sphere of strange matter, a cosmic goo. For decades, this remained a chilling piece of theoretical physics, a ghost story to be told by cosmologists in dimly lit lecture halls. After all, if this stuff is so stable, where is it? Why hasn't the entire universe already been converted? Perhaps the energy barrier to kickstart its formation is simply too high. Perhaps it can only be forged in the most violent and extreme crucibles the universe can offer. And so we look back to the heavens with a new and dreadful sense of purpose. We look to the cosmic graveyards, to the collapsed cores of massive stars that have died in supernova explosions. We look to neutron stars. These are objects so dense that a teaspoon of their material would outweigh a mountain. They are in essence city-sized atomic nuclei. Here in their cores, the pressures might be great enough to crush neutrons into that sea of quarks to brew the first drops of strange matter. Perhaps some neutron stars are not neutron stars at all. Perhaps they have already undergone the conversion and are in fact giant, strange stars silently spinning in the darkness. And what happens when two such objects, two of the universe's most extreme creations, collide? The gravitational waves from such an impact would ripple across the cosmos, but the collision itself would be an event of unimaginable violence, flinging debris across interstellar space. Debris that could include not just ordinary matter but microscopic droplets of their strange cause. Strangelets, cosmic seeds of conversion launched like shotgun pellets across the galaxy. Sleeper agents traveling at incredible speeds through the void for millions of years, waiting for the moment they encounter a precarious world. A world resting peacefully on the mountainside, unaware that the slightest touch could send it tumbling into the valley below. The hypothesis is on the table. The potential forgers have been identified. Now the search begins, a search not just for a new type of matter, but for a verdict on our own cosmic fragility. Are we safe, or are we living on borrowed time, oblivious to the cosmic bullets that may already be on their way? And so we arrive at the question that haunts the very edges of this new physics, the shadow that falls across every equation. Describing the strange heart of matter, we have found a substance theoretically more stable than anything in our universe, a perfect configuration of cosmic ingredients. But perfection, we have learned time and again, can be a terrifyingly aggressive force. The danger here is not one of explosive energy, not a flash of light and heat, but something far more insidious, a threat that operates on the level of existence itself. It was a fear given a name not by a physicist, but by a novelist. Kurt Vonnegut, in his masterpiece, Time's Cat's Cradle Times, imagined a substance called Ice-9, a new form of water with a higher melting point. A single tiny seed crystal of this material, if dropped into the ocean, could teach every water molecule it touched how to rearrange itself into this more stable frozen state, triggering a chain reaction that would encase the entire planet in ice. It was a brilliant, chilling piece of science fiction. Yet deep within the mathematics of quantum chromodynamics, physicists began to see the ghost of a real-world Ice-9, a monster born not of water, but of the quarks that build our reality. This is the central terror of the Strangelet, its potential role as a catalyst for cosmic assimilation. Imagine a single microscopic strangelet no larger than an atomic nucleus hurtling through space. If the hypothesis holds true, this tiny bullet possesses a power of conversion so absolute it borders on the mythological. Should it strike a normal nucleus, the heart of an atom of oxygen, in our air, or carbon in your own body, it doesn't annihilate it, it doesn't shatter it. It times converts times it. The encounter is not a collision but an act of contagion. The Strangelet, with its perfect trio of up, down, and strange quarks, represents a lower, more comfortable energy state. When it makes contact, the immense pressure of the strong nuclear force provides a pathway for the ordinary protons and neutrons to transform. An up quark might be squeezed into a down quark. A down quark under this extraordinary influence could be pressured into becoming a strange quark. The original nucleus, once a familiar building block of our world, would be rewritten, its internal code overwritten to match the Strangelet's template. And in that conversion, it would release a small puff of energy, and most terrifyingly, it would become part of the growing Strangelet. The process would not stop. This newly enlarged Strangelet, now slightly more massive, would continue its journey, and the next nucleus it met would suffer the same fate, and the next, and the next. It's a domino cascade at the subatomic level, a single wrong note that forces the entire orchestra of matter to retune itself to a new silent key. If such a malevolent seed were to strike the Earth, it would not be an impact we would see, but a change we would times become asterisk. It would begin its work instantly, converting the matter of our planet's core, our mantle, our crust. The effect would propagate outwards at nearly the speed of light, a wave of pure transformation. The ground beneath your feet would cease to be silicon and iron and nickel. It would become strange matter. The air would cease to be nitrogen and oxygen. It would become strange matter. Every book, every mountain, every ocean, every living thing would be systematically and completely disassembled at the quark level and reassembled into a single planetary-sized sphere of inert, ultra-dense, strange matter. There would be no explosion to mark our passing, no final dramatic fireball. Just a quiet, relentless conversion. The Earth, our vibrant, chaotic, living world, would, in a matter of minutes, be reduced to a perfectly stable, perfectly featureless, and perfectly dead orb of exotic goo, a strangelet a few dozen kilometers across, silently orbiting the sun as a tombstone for humanity. This apocalyptic scenario, however, hinges on one crucial, tantalizing, and ferociously debated condition. It relies on the absolute stability of strange matter. For this conversion to occur, the strangelet cannot simply be a fleeting transient particle that decays in a fraction of a second. It must be what physicists call absolutely stable, meaning it represents the one true ground state of all nuclear matter. It must be, in essence, the universe's preferred way of being. Think of it like a valley surrounded by mountains. Our normal atomic nuclei, the protons and neutrons that make up everything we know, are like villages nestled in a high mountain valley. They are stable, yes, in the sense that they are not actively rolling downhill. They have found a comfortable place to exist. But the Strangelet hypothesis proposes that over the next mountain range, there is a much deeper valley, a vast coastal plain at sea level. This is the true ground state, the lowest possible energy. As long as our villages in the high valley are left alone, they remain stable. But if a single traveller, a Strangelet, arrives from that great coastal plain, it carries with it the map. It shows the way down. By its very presence, it provides the pathway for everything in the high valley to tumble down into that lower, more stable state, a place from which there is no return. The entire existence of our universe as we know it, therefore, might be a cosmic accident. We may be living in a state of what is called metastability, like a carefully balanced rock on a cliff edge, stable for now but vulnerable to the slightest nudge. The universe we perceive, with its 100-odd elements and complex chemistry, might just be a temporary phase, a cosmic froth that will eventually settle into its true strange form once the settling process is initiated. This profound and unsettling idea leads to a critical question. If strange matter is so stable, why isn't the universe already made of it? Why are we here at all? The answer, theorists believe, lies in the difficulty of its creation. To form even a tiny strangelet requires immense energy and pressure conditions so extreme that they are found only in the most violent crucibles of the cosmos, or perhaps in the hearts of our most powerful machines. Furthermore, for a strangelet to survive and grow, it must exist within a very specific stability window. If it's too small, with only a handful of quarks, quantum effects cause it to be unstable, and it would rapidly decay back into ordinary particles. It must achieve a certain critical mass before its collective structure, its lower energy state, can protect it from falling apart. Conversely, if the conditions for stability require an enormous strangelet one with millions or billions of quarks, then it's unlikely one would ever form spontaneously. The danger, the true nightmare fuel for physicists, lies in the possibility of a stability window that starts with a relatively small number of quarks, perhaps a few dozen or a few hundred. Such a particle would be small enough to be potentially created, yet large enough to be absolutely stable and begin its voracious consumption of the world around it. Determining the boundaries of this window, figuring out if it even exists, became one of the most urgent and controversial quests in modern physics. The question was no longer purely academic. As humanity began to build machines capable of replicating the infernal conditions of the early universe, we were no longer just observing the cosmos. We were gaining the power to tamper with its fundamental architecture. And we had to wonder if in our relentless quest for knowledge, we were about to knock that precariously balanced rock off the cliff edge. The theoretical fear was about to become a terrifyingly practical concern. The late 1992. On Long Island, New York, a colossal new machine was taking shape, a testament to human ingenuity and our insatiable desire to understand our origins. The Relativistic Heavy Ion Collider, or RHIC, was a 2.4-mile ring of superconducting magnets and sophisticated detectors, a scientific cathedral designed for a single extraordinary purpose: to smash atoms together with such violence that they would momentarily melt. For a few fleeting trillionths of a second, the collision of two gold nuclei traveling at 99.995%, the speed of light, would generate temperatures 250,000 times hotter than the center of the sunday. In that fleeting fireball, protons and neutrons would dissolve into their constituent parts, creating a primordial soup of quarks and gluons, the very state of matter that is thought to have existed in the first microsecond after the Big Bang. It was a time machine to the dawn of creation, a window into the birth of the universe. It was also, in the minds of a concerned few, potentially the most dangerous machine ever built. As the first experiments at RHIC drew near, a tremor of anxiety began to ripple through the scientific community and out into the public sphere. The question was, simple and stark, what if, in creating this quark-gluon plasma, we accidentally crossed the threshold for creating a stable, negatively charged strangelet? The gold nuclei being smashed together were rich with up and down quarks. The immense energy of the collision could easily create pairs of strange and anti-strange quarks. In the chaotic maelstrom of the fireball, what if a small cluster of up, down, and strange quarks happened to coalesce in just the right configuration to fall into that hypothetical low-energy valley? What if out of a billion collisions, just one produced a single stable seed of strange matter? The creators of RHIC argued that the energies involved, while immense by our standards, were still far below those seen in natural cosmic ray collisions, which have been bombarding the moon and other celestial bodies for eons without turning them into strange matter. The moon, they pointed out, is still there. This became known as the astrophysical argument, a safety net woven from cosmic observation. But a counter-argument quickly emerged, subtle and deeply worrying. A strangelet created at RHIC would be different from one created by a cosmic ray hitting the moon. A cosmic ray collision is a violent, explosive event. Any strangelet formed would likely be sent flying with enormous velocity ejected back out into space before it had a chance to do any damage. The experiments at RHIC, however, were different. They were designed to bring two massive nuclei to a crashing halt, creating a relatively stationary, dense fireball. If a strangelet were formed in this environment, it could be created with very little momentum. It might emerge from the wreckage nearly at rest. A slow-moving, negatively charged strangelet would be the ultimate predator. It would be gravitationally bound to the Earth, unable to escape. Its negative charge would draw in the positive nuclei of the surrounding atoms in the detector, guaranteeing a steady supply of food to begin its catastrophic conversion process. The machine built to unlock the secrets of the universe could become the very instrument of our planet's destruction, a self-inflicted wound on a planetary scale. The debate spilled out of the closed doors of physics departments and onto the pages of newspapers and magazines. Headlines blared with dire warnings, the Big Bang machine that could destroy the Earth. Television specials featured computer-generated graphics of our planet shrinking into a tiny, dense ball. The public, already primed by decades of Cold War anxiety and tales of scientific hubris, latched onto the narrative. It was a story as old as time humanity, in its arrogance meddling with forces it did not understand. RHIC became a focal point for a deep-seated fear of our own power. Lawsuits were filed to halt the collider's operation, citing the potential for a global catastrophe. Frank Wilczek, a Nobel laureate who had done foundational work on the theory, was quoted as saying the chances of disaster were low, but the stakes were quite literally the world. An article in Times Scientific American Times in 1999 laid out the threat in chilling detail, lending mainstream credibility to what had once been a fringe concern. The scientists at Brookhaven National Laboratory, where Rick was located, found themselves in an unprecedented position. They weren't just conducting an experiment, they were forced to publicly defend the continued existence of the planet against their own creation. They convened safety panels, published detailed risk assessments, and double and triple-checked their calculations. The consensus remained that the risk was infinitesimally small, practically zero. They refined the astrophysical argument, showing that neutron stars, which are constantly bombarded by energies far exceeding Rick's, are still around. If strangelet conversion were easy, the universe should be littered with strange stars, but we see none. They argued that the quark-gluon plasma created would be so hot that any fledgling strangelet would be instantly torn apart before it could cool down and stabilize, like trying to form a snowflake in a blast furnace. Every theoretical model, every piece of observational data pointed to safety. And yet the doubt lingered. The models were, after all, just models. Our understanding of the strong nuclear force, while powerful, was still incomplete. There was a difference between believing the probability of disaster was 1-0 to the minus something and knowing with absolute certainty that it was 0. And no one could claim absolute certainty. The human mind is not well equipped to handle infinitesimal probabilities when the consequences are infinite. And so, in the summer of 2000, the moment of truth arrived. The engineers and physicists in the RHIC control room made their final checks. All across the world, a small community of people held their breath, caught between the thrill of discovery and a sliver of primal fear. The countdown began. The magnets hummed with unimaginable power, guiding 2 beams of gold ions in opposite directions around the Great Ring, accelerating them closer and closer to the speed of light. They were photons away from the ultimate speed limit, their mass swollen by the strange magic of relativity. Then the order was given. The beams were steered into a collision course. For the first time, a man-made machine was about to create the stuff of the newborn universe. The operators watched their screens. The detectors registered a storm of particles, a beautiful chaotic spray of energy and matter blossoming from the point of impact. The experiment had worked. Data began pouring in. The planet continued to spin. The air in the control room remained breathable. The ground beneath Long Island remained solid. There was no catastrophic conversion. The world had not ended. A collective sigh of relief, both in the control room and around the global physics community, was almost palpable. The experiment was a stunning success, opening up a whole new field of physics, and it had been done safely. The safety committees were vindicated. The models, it seemed, were correct. But the question had not been fully erased. It had merely been pushed back. We had survived our own experiment, our own tentative knock on a forbidden door. RHIC, and later the even more powerful Large Hadron Collider in Europe, would go on to perform trillions upon trillions of collisions without incident, making the Strangelet doomsday scenario from particle accelerators seem increasingly remote. We had looked into the abyss of our own creation and found it empty. Yet this newfound confidence came with a profound and humbling realization. We had confirmed that times were not yet capable of building a weapon that could unmake the world at a fundamental level. Our technology, as mighty as it seemed, was still dwarfed by the power of the cosmos itself. The safety of our world was not guaranteed by our own restraint or wisdom, but by the sheer brute force of nature's ongoing experiments. This leaves us with a far more unsettling question. We may have dodged the bullet we made for ourselves, but what about the bullets the universe has been firing for 13 billion years? If our own colliders are too feeble to forge a world-ending strangelet, are we truly safe? Or does that simply mean we have been looking in the wrong place for the bringer of our end, searching our own hands for a weapon that is perhaps already falling from the sky? And so this terrifying potential, born in the abstract equations of nuclear physicists, was no longer confined to the chalkboard. What had been a whisper in the hushed halls of academia, an esoteric footnote in the grand story of the cosmos, was about to become a global shout. The theoretical monster was clawing its way into our world, and its arrival was heralded not by a cataclysm, but by the hum of machinery and the laying of concrete on a quiet stretch of Long Island, New York. This was the dawn of the Relativistic Heavy Ion Collider, or RHIC. For the scientists at Brookhaven National Laboratory, it was a time machine, a magnificent instrument designed to smash gold ions together with almost unimaginable force. Their goal was nothing less than to rewind the cosmic clock, to recreate for a fleeting, infinitesimal moment the very conditions of the universe in its first microseconds of existence. They sought to liberate quarks and gluons from their eternal imprisonment inside protons and neutrons, to witness the birth of the primordial quark-gluon plasma, the incandescent soup from which all matter would eventually condense. It was a noble, profound quest to understand our own origins, but to a small, growing number of observers, this was not a quest for knowledge. It was the forging of a key to Pandora's box. The first tremors of public apprehension were subtle, appearing in niche publications and the nascent forums of the early internet. They were questions at first seeded by a handful of concerned physicists and science writers. If you are creating the universe's most extreme state of matter, what guarantees do you have that you will not also create its most dangerous state? The logic, when laid bare for a non-scientific audience, was chillingly simple and tête presse, impossible to ignore. We had just learned about the Strangelet, this hypothetical nugget of perfectly stable, perfectly predatory matter. We had just been told that if one were to appear, it would begin a chain reaction converting everything it touched into more of itself in a slow-motion apocalypse. And now an enormous billion-dollar machine was being built with the express purpose of creating exotic, unknown forms of matter by simulating the most violent event imaginable, the Big Bang itself. The connection was not difficult to make. It was a straight line drawn between a theoretical nightmare and a tangible physical machine. The fear had found its focal point, its ground zero. The narrative began to crystallize, one that was far more powerful and visceral than any paper on quantum chromodynamics. It was a story of hubris, of scientists playing God of humanity, building its own cosmic self-destruct button without fully understanding the wiring. The media, sensing a story of epic proportions, descended. What began as a scientific curiosity soon morphed into a maelstrom of sensational headlines. Doomsday Machine on Long Island, one tabloid screamed. Scientists gamble with fate of the Earth, proclaimed another. Television news segments juxtaposed complex diagrams of the collider with dramatic artist-rendered animations of the planet dissolving into a featureless grey sphere. They called it the Ice Nine scenario, borrowing from Kurt Vonnegut's novel, a perfect, terrifyingly simple analogy that lodged itself deep in the public consciousness. It didn't matter that the physics was complex. The consequence was not. You didn't need a doctorate to understand what total annihilation meant. This media frenzy created a feedback loop. The more the public worried, the more the media covered the worry, which in turn generated even greater anxiety. Suddenly, physicists at Brookhaven found themselves fielding calls not from fellow academics, but from panicked local residents, from furious radio talk show hosts, and from journalists who framed every question as an accusation. Their work, once a source of pride and intellectual passion, was now being portrayed as reckless, a cavalier gamble with the lives of every man, woman and child on the planet. They were no longer seen as explorers, but as potential architects of our doom. This unprecedented wave of public fear soon coalesced into organized opposition. Petitions circulated online, gathering hundreds of thousands of digital signatures from around the globe. Protest groups, once focused on more terrestrial concerns, now turned their attention to the existential threat they believed was quietly assembling in Upton, New York. But the most shocking development, the one that truly marked this as a turning point in the relationship between science and society, came not in the form of a protest sign, but of a legal summons. Lawsuits were filed. You have to understand how truly extraordinary this was. Citizens were taking a fundamental physics experiment to court, demanding that a judge, a person of law, issue an injunction against the exploration of the subatomic world. The courtroom, a place designed to weigh evidence of earthly disputes, was suddenly being asked to adjudicate on the potential for planetary destruction based on theoretical physics. One lawsuit filed in federal court sought to halt the activation of RIC, arguing that its operation posed an unacceptable risk to the entire planet, and that the laboratory had failed to provide an adequate environmental impact statement. The absurdity of the situation was staggering. How do you quantify the environmental impact of non-existence? How do you cross-examine a theory of quantum mechanics? A legal system built on precedent and verifiable fact was now grappling with a danger that was by its very nature purely hypothetical but infinitely consequential. For the scientific community, this was a moment of profound shock. Their initial reaction was one of dismissal, even a degree of academic arrogance. They saw the fears as the product of misunderstanding of science fiction polluting public discourse. They tried to explain the minuscule probabilities, the infinitesimal timescales, the energy densities involved, but they quickly discovered that their language, the language of mathematics and peer-reviewed certainty, was utterly powerless against the raw emotional force of existential dread. A 1 in a billion chance to a physicist is practically zero. To a parent lying awake at night, it is a chance. And when the stakes are everything, any chance at all feels unacceptable. The scientists of Brookhaven, and indeed the entire high-energy physics community, were forced into a position they had never experienced before. They were on the defensive, compelled to justify their very pursuit of knowledge to a terrified and skeptical world. It was no longer enough to publish their findings in academic journals. They had to face the public. They had to create formal safety reports, documents, written not just for their peers, but for judges, for politicians, and for the average citizen. They had to prove a negative. They had to prove beyond a reasonable doubt that their machine would times not times destroy the planet. This was the birth of the RHIC Safety Assessment Report, a landmark document that represented the first time a major scientific body had to formally and publicly litigate the survival of the human race against its own experiment. Just as the furor over RHIC began to settle as its successful and uneventful operation seemed to calm the most immediate fears, a new, far greater shadow began to loom on the horizon. Across the Atlantic on the Franco-Swiss border, a project of truly monumental scale was underway. If Rick was a time machine, this new instrument was a veritable Big Bang generator. It was the Large Hadron Collider, the LHC. It was 27 kilometers in circumference, buried 100 meters beneath the Earth. A ring of superconducting magnets, cooled to a temperature colder than deep space. Its purpose was to accelerate protons to 99.9999991% the speed of light, and smash them together with energies 7 times greater than RHIC. The scale was breathtaking, the ambition historic. It promised to find the elusive Higgs boson, to probe the mysteries of dark matter, to perhaps uncover entirely new dimensions of space-time. But with its vastly greater power came a vastly greater fear. All the anxieties that had swirled around RHIC were now magnified 1,000-fold and projected onto the LHC. The Doomsday Machine wasn't on Long Island anymore. It was in the heart of Europe, and it was an order of magnitude more powerful. The controversy surrounding the LHC was a global inferno compared to the RHIC brushfire. The internet, now a far more mature and pervasive force, became the central nervous system for the opposition. Websites with names like LHC Critique and Stop CERN sprang up, becoming repositories for every fear, every doubt, every dissenting scientific opinion, no matter how fringe. The Strangelet problem was back, but this time it had company. New apocalyptic scenarios were added to the list. What if the LHC created a microscopic black hole that, instead of evaporating as theory predicted, became stable and devoured the Earth from the inside out? What if it created something even more bizarre, a magnetic monopole that could catalyze the decay of protons and unravel the very fabric of matter? These were theoretical spectres, ghosts in the quantum machine, but in the court of public opinion, they were treated as imminent threats. Another lawsuit was filed, this time with the European Court of Human Rights, arguing that the 20-member nations of CERN were violating their people's fundamental right to life by commissioning such a dangerous experiment. The case, led by a small group of thinkers, argued that the scientists, for all their confidence, were operating at the very edge of human knowledge. Out on that frontier, they argued certainty is a luxury you do not have, and a misstep could be the last one humanity ever makes. This time, the scientists knew they couldn't remain cloistered in their labs. The challenge was direct, public, and global. The leaders of the LHC project, brilliant physicists who were on the cusp of the greatest discoveries in a generation, found themselves spending an inordinate amount of their time not analyzing data but acting as public relations officers, as crisis managers, as therapists to a frightened world. They appeared on television news programs, engaged in heated public debates, and wrote countless articles and op-eds. They patiently explained time and again the concept of Hawking radiation that should cause any micro black hole to vanish in a puff of energy. They reiterated with a confidence that their critics mistook for arrogance the infinitesimally low probability of producing a stable, negatively charged strangelet. But with every reassurance, They encountered the same fundamental unanswerable response, but are you absolutely 100% certain? Can you guarantee it? And of course they could not. Science does not deal in absolute certainty. It deals in probabilities, in evidence, in theories tested to their breaking point. There is always a margin of error, always a frontier beyond which lies the unknown. And it was in this sliver of uncertainty, this razor-thin margin between what we knew and what we didn't, that the global fear took root and flourished. The LHC Safety Assessment Group was convened a committee of independent physicists tasked with a burden of proof unlike any other in scientific history. They were not just checking calculations or verifying engineering tolerances. They were, in essence, putting the laws of physics themselves on trial. They had to construct an argument so robust, so utterly convincing, that it could placate the global panic and allow the greatest experiment in history to proceed. They were being asked to deliver a verdict on our continued existence. The world watched, holding its collective breath. The date for the LHC's first beam was set. The lawsuits were proceeding through the courts. The media was in a frenzy. For one unprecedented, surreal moment in our history, the esoteric world of quantum field theory and the fate of every living thing on Earth became inextricably linked in a dramatic public spectacle. The question was no longer a theoretical one. As engineers prepared to flip the switch, a very real decision had to be made. Would we press forward into the unknown, driven by our insatiable curiosity, or would we flinch, pulling back from the precipice of a discovery that might also be our oblivion? The physicists believed they had the answer, an argument not from theory alone, but from the cosmos itself. They claimed that nature had already run this experiment for us billions of times over, and that the evidence of our survival was written in the stars. But first, they had to make the world listen. While the headlines screamed and the world held its breath, a very different story was unfolding inside the very laboratories accused of building a doomsday device. It was a narrative told not with fear but with physics, a quiet, methodical dismantling of the nightmare, one rigorous calculation at a time. The spectre of a Strangelet chain reaction, of an unstoppable conversion of our world into a featureless orb of quark matter, demanded more than just dismissal. It demanded proof. The scientific community, faced with a question that touched upon the very foundations of existence, turned its collective intellect to the problem, not to reassure the public with platitudes, but to reassure itself with the unassailable logic of the cosmos. They returned to the first principles of creation, re-examining the crucible where strange matter might be born, and found that the universe itself had built powerful, almost insurmountable firewalls against its own accidental annihilation. The terror they would discover was not in the physics, but in a profound misunderstanding of it. The very first line of defense is a barrier of pure brute force. To even begin to imagine forging a stable strangelet, you must first create the raw ingredient, a state of primordial reality known as the quark-gluon plasma. This is not merely a matter of heating something up. It is an act of cosmic violence that seeks to replicate the first millionth of a second after the Big Bang. In that fleeting instant, the universe was so unimaginably hot and dense that the protons and neutrons we know today could not exist. They were dissolved into a seething, turbulent ocean of their constituent quarks and the gluons that bind them. To create this state on Earth inside the circular tunnels of an accelerator requires a feat of incredible engineering. We take atoms, heavy ions like gold or lead, strip them of their electrons and accelerate them to within a whisper of the speed of light. They circle for millions of miles, gathering kinetic energy, until they become relativistic sledgehammers, each nucleus weighing more than a stationary battleship. Then we crash them together. The collision is an event of such concentrated energy that the temperature inside the impact zone skyrockets to over 4 trillion degrees Celsius. That's 250,000 times hotter than the core of our Sunday. For a sliver of a moment, for a duration so short, it beggars belief, about 10 to the minus 23 seconds, the protons and neutrons literally melt. Their internal structure dissolves, releasing the up and down quarks, and the immense energy of the collision materializes new particles from the vacuum, including the heavier, more exotic strange quarks. For this briefest of instants, a microscopic droplet of the early universe flickers into existence here on Earth. This is the theoretical furnace where a strangelet could be forged. But this is also where the doomsday scenario begins to unravel, confronting its first impossible hurdle. The hypothesis of strange matter stability rests on a delicate, razor-thin condition that a clump of up, down, and strange quarks would possess a lower energy state, a more profound stability than the familiar matter of protons and neutrons. Think of it like water seeking its lowest level. If strange matter is that lowest level, then everything else should eventually want to convert into it. Yet creating this state isn't like rolling a ball downhill. It's like trying to force a river to flow up and over a mountain range to reach a hypothetically lower valley on the other side. That mountain range is the colossal energy barrier. You don't just need to create strange quarks, you need to create enough of them in a small enough volume, and you need them to cool down and settle into a stable configuration before they decay or fly apart. The energy required to overcome the powerful forces that keep quarks bound inside protons to melt that structure and then to calmly reassemble it into a new, more stable form is monumental. It's a precise, multi-stage process that nature seems to abhor. Our colliders can provide the initial shock, the raw heat to create the plasma, but they cannot provide the gentle, sustained pressure and the specific cooling conditions needed for this new state of matter to crystallize. It's the difference between a lightning strike hitting a sand dune and the millennia of geological pressure required to form a flawless diamond. The lightning strike is violent and spectacular, creating fleeting glass, but it lacks the sustained specific force needed for true transformation. Our particle accelerators are the lightning strike, not the mountain. They produce the flash, the heat, the raw ingredients, but the conditions are simply wrong for building a lasting structure. The very act of creation is so violent, so explosive, that it becomes its own undoing. This leads us to the second great firewall, a defense written into the very speed of subatomic interactions. Let us return to that microscopic inferno, that droplet of quark-gluon plasma. For that infinitesimal moment it exists, it is a chaotic maelstrom. It is not a calm pond where new structures can gently form. It is a supernova, in miniature, an outward exploding fireball of pure energy and fundamental particles. The pressure from within is overwhelming, and it expands at nearly the speed of light. The particles born in this cataclysm, the up, down, and strange quarks, the gluons, the fleeting exotic cousins, are thrown outwards with incredible force. They are shrapnel from a quantum explosion. The idea that a stable strangelet could form here requires the freshly minted strange quarks to somehow find each other amidst this chaos, to link up with the right number of up and down quarks, and to form a stable bound state all before the fireball dissipates. The time frame for this to happen is measured in yoctoseconds. A yoctosecond is to 1 second what 1 second is to the entire age of the universe. It is a duration so profoundly short that light itself can barely cross the width of a single proton. Within this impossible window of time, the quark-gluon plasma has already cooled and expanded to the point where the quarks are recaptured into familiar particles. The strong nuclear force reasserts its dominance, and the quarks hadronize, snapping back into the protons, neutrons, pions, and kaons that our detectors actually see streaming from the collision point. There is no lingering nugget of strange matter. There is no seed of destruction. The fireball simply evaporates. It's like throwing a deck of cards into a hurricane and expecting them to land perfectly ordered into a house of cards. The forces of dispersal are infinitely stronger and faster than the forces of assembly. The experiments at RHIC and the LHC have run trillions of these collisions, meticulously analyzing the debris from every single one. They have found a perfect confirmation of the standard model of particle physics, a beautiful spray of known particles that matches our theories with stunning precision. What they have never ever seen is a candidate for a stable multi-quark object emerging from the wreckage. The monster simply doesn't have time to be born. The crucible in which it might be forged is also the explosion that tears it to pieces before it can ever truly form. It's a self-dismantling bomb, a threat that contains the seeds of its own immediate annihilation. But let us, for the sake of argument, push past these two colossal barriers Let us imagine that against all odds a microscopic stable strangelet times is times formed. A tiny seed of this new reality forged in the collider's fire now exists. Does our world begin to end? The answer again appears to be a resounding no, thanks to a more subtle but equally powerful defense mechanism, the physics of electric charge. For a strangelet to begin its catalytic conversion of Earth, it must be able to interact with the matter around it. The matter of our world is made of atoms which consist of a positively charged nucleus surrounded by a cloud of negatively charged electrons. To consume a nucleus, the strangelet must first get close to it. The initial, most terrifying versions of the doomsday scenario assumed that strangelets would be strongly negatively charged. This would make them irresistible cosmic predators. They would exert a powerful electrostatic pull on the positive nuclei of atoms, drawing them in like moths to a flame, effortlessly overcoming the electron clouds and initiating the conversion process. A negatively charged strangelet would be the perfect killer. However, as our understanding of quark matter deepened, this assumption crumbled. More sophisticated models, taking into account the complex interplay of quark masses and quantum chromodynamics, began to predict the opposite. A small, stable strangelet, if it could exist at all, would likely have a net times positive times charge. This completely flips the script. Instead of being an irresistible attractor, a positive strangelet becomes a cosmic pariah. As it approaches an atomic nucleus, which is also positively charged, it would be met with a powerful wall of electrostatic repulsion. Like trying to force the north poles of two powerful magnets together, the two objects would violently repel each other. The strangelet would be unable to get close enough to initiate a conversion. It would simply bounce off the atoms in its path, a lonely wanderer, incapable of interacting with the world around it. It would be a key that doesn't fit a single lock in the universe. Even if the strangelet were perfectly neutral, the situation isn't much better for the doomsday theorists. A neutral strangelet would still have to contend with the atom's protective electron cloud. Without a strong attractive charge to pull the nucleus out, the strangelet would have to physically blunder its way through this electronic shield, a task that is far from simple at the quantum scale. The physics of charge, once thought to be the engine of destruction, instead provides a fundamental shield. The very nature of the strangelet, its most likely configuration, would render it impotent, a ghost passing harmlessly through the substance of our world. These arguments, the immense energy barrier, the instantaneous fireball dispersal, and the conundrum of electric charge form a powerful interlocking defense. They suggest that creating a dangerous strangelet in a collider is not just improbable but borders on the physically impossible. Yet there remains one final piece of evidence, one that moves beyond the realm of theoretical physics and into the domain of cosmic observation. It is an argument so profound and so elegant that many scientists consider it the final word on the matter. It is the silent, ongoing testimony of the universe itself. For 4.5 billion years, the Earth has been adrift in a cosmic shooting gallery. Our planet, along with our moon and every other body in the solar system, has been relentlessly bombarded by cosmic rays. These are not the gentle rays of the sun. They are subatomic particles, protons, helium, nuclei, heavier ions, accelerated to unimaginable energies by the most violent events in the cosmos, by supernovae, by the swirling accretion disks of black holes, and by the turbulent hearts of distant galaxies. They are the universe's own particle accelerator, and its power dwarfs anything we could ever hope to build. The highest energy cosmic rays ever detected carry the kinetic energy of a well-pitched baseball, all concentrated into a single infinitesimal proton. When one of these cosmic bullets slams into the upper atmosphere, it impacts an oxygen or nitrogen nucleus with a center of mass energy many, many times greater than what is achieved at the Large Hadron Collider. This is not a rare occurrence. It happens thousands of times a second all over the globe. Every second of every day for billions of years, nature has been running the Strangelet experiment for us with energies we can only dream of. The collisions happening constantly above our heads are far more likely to have the right conditions for strangelet formation than our own carefully controlled head-on impacts. And the target is not a heavily shielded detector underground. The targets are the Earth itself, and even more tellingly, the Moon. The Moon is the perfect witness. It has no thick atmosphere to slow down incoming cosmic rays, and no magnetic field to deflect them. For eons it has been sitting there, a pristine passive collector, absorbing the full unmitigated fury of the cosmos. If stable, dangerous strangelets were a natural consequence of high-energy particle collisions, the universe would have already made them. They would have been forged in the atmosphere of Earth or upon the sterile plains of the Moon. A single successful conversion event on the Moon would have been catastrophic and undeniable. The chain reaction would have propagated through the lunar rock, transforming our celestial companion into a dense, dark sphere of strange matter, a so-called strange star, in a matter of hours or days. We would look up at the night sky and see not the familiar cratered face of the Moon, but a bizarre, tiny and impossibly heavy object, its gravitational influence profoundly altered. Jupiter, with its immense size and powerful magnetic field funneling particles into its atmosphere, would have been an even more likely victim. Yet when we look out into our solar system, we see normalcy. We see rock and gas and ice all composed of the same mundane protons and neutrons that make up our own bodies. The universe has been running the most extreme version of this experiment for longer than the Earth has existed, and the results are in. We are still here. The Moon still shines. Jupiter still reigns. This cosmic silence, this profound lack of evidence for strange matter conversion anywhere we look, is the most powerful reassurance of all. It suggests that our planet is protected by a kind of celestial immune system, one where the fundamental laws of physics themselves prevent the formation of such a cosmic contagion. The nightmare of the Strangelet, it seems, is a ghost story the universe has already told us has no monster at the end. And so we stand at the precipice gazing into the theoretical abyss that we have spent our journey mapping. We have charted the strange quantum shoreline of quark-gluon plasma, navigated the violent stellar cataclysms that might forge it, and listened to the whispered fears of a particle that could rewrite existence. The question, once a fringe speculation, now hangs heavy in the air, echoing in the heart of our most ambitious experiments. Could a microscopic seed of strange matter, a single malevolent strangelet, truly act as the trigger for our own annihilation? Could it be the agent of a planetary conversion, a chain reaction that transforms our vibrant blue world into a dead, the featureless orb of exotic goo? The fear is primal tapping into our deepest anxieties about forces beyond our control of an enemy, not from the stars, but from the very rulebook of the universe itself. To answer this, to truly confront this ultimate terror, we cannot rely on instinct or on hope. We must turn to the cold, hard logic of physics, to the intricate web of laws that govern every interaction from the dance of galaxies down to the ephemeral flicker of a quark. Here, in the unyielding mathematics of reality, we find our shield. The doomsday scenario, for all its cinematic horror, must pass through a series of extraordinarily narrow gates, each one guarded by a fundamental principle of the cosmos. Failure at any single gate means the chain reaction never begins. The threat evaporates. And as we examine these gates one by one, a story of profound unlikelihood of built-in cosmic safety begins to emerge. It is a story not of doom, but of the universe's own subtle and robust architecture. The first gate is perhaps the most absolute, a simple question of energy and stability. For a strangelet to be a threat, for it to consume an atomic nucleus and convert its quarks, the final strange matter configuration must be a more stable, lower energy state than the original nucleus. Think of it like a ball perched at the top of a hill. The ball is stable enough, but if a deeper valley exists nearby, a little nudge is all it takes to send it rolling down to a more fundamentally stable position. In the world of particles, this deeper valley is known as higher binding energy. The protons and neutrons in an iron nucleus, for instance, are bound together more tightly than in almost any other element residing in a very deep and stable energy valley. For a strangelet to convert iron, it would need to offer a state of matter that is in an even times, deeper times valley, a state of such profound stability that it represents the undisputed ground floor of all hadronic matter. This idea, known as the Bodmer-Witten hypothesis, is the very foundation of the strangelet threat. Yet this absolute stability is not a given, it is a delicate theoretical proposition. Physicists believe that if strange matter is stable at all, its stability exists only within an incredibly narrow range of physical parameters, a stability window. Imagine a tightrope walker poised between two skyscrapers. One building represents the realm of ordinary matter, the other a state where strange matter is so stable it would have already become the dominant form of matter in the universe. The tightrope itself is that tiny hypothetical window where strange matter is just times stable enough to exist, but not so stable that it's everywhere. The calculations that define the width of this rope depend on precise values, like the mass of the strange quark and the strength of the force that binds quarks together. These are not numbers we can simply look up in a book. They are fundamental constants of nature, whose interplay we are still working to fully understand. Our best estimates, drawn from decades of particle physics experiments, suggest that this window of stability, if it even exists, is extraordinarily slender. It is entirely possible and even plausible that the window is closed shut, that no configuration of strange matter is truly more stable than a simple iron nucleus. In this case, strangelets would be nothing more than fleeting high-energy curiosities. They would be like a ball kicked to the top of a hill, destined to immediately roll back down. A strangelet made of a few dozen quarks might flicker into existence for a trillionth of a second inside a particle collider, a momentary quantum phantom, only to decay back into ordinary particles, releasing its excess energy. It would be an artifact of the collision, not a seed of destruction. The universe might simply have no deeper valley for matter to fall into. The first and most critical gate, the gate of stability, may very well be sealed forever, but for the sake of our journey, let us grant the premise. Let us imagine that nature has been unthinkably precise, that the constants of the universe are tuned to perfection, and that this quantum tightrope, this stability window, does indeed exist. A stable strangelet is possible. It can be made. Even so, the apocalypse is not yet upon us. A second and perhaps even more formidable guardian stands in its path, the fundamental force of electromagnetism. To understand this defense, we must visualize the strangelets target the nucleus of an atom. A nucleus is a tightly packed ball of positive charge made of its protons. It is surrounded by a cloud of negatively charged electrons, but the heart of the atom is an impregnable fortress of positive repulsion. To get close to it, you must overcome this ferocious electrostatic barrier, a force field that grows exponentially stronger the nearer you approach. Any particle that wishes to interact with and convert a nucleus must first get close enough for the short-range strong nuclear force to take over. This is where the strangelet's own electric charge becomes the single most important factor in its potential lethality. Let's consider the possibilities. If a strangelet were positively charged, its fate would be sealed before its mission ever began. Like two powerful magnets turned to repel each other, the positive strangelet and the positive nucleus would violently push each other away. The strangelet would be deflected, cast aside by the very target it sought to consume. It would never get close enough to initiate a conversion. The electrostatic sentinel, the Coulomb barrier, would guarantee the nucleus's safety. A positively charged strangelet is for all intents and purposes entirely harmless to bulk matter. What if the strangelet were electrically neutral? This seems more dangerous. Without a charge, it would not be repelled. It could drift toward a nucleus, immune to the electrostatic force field. Yet even here, nature has provided a subtle defense. While a neutral strangelet wouldn't be repelled, it also wouldn't be times attracted *. Its path through matter would be a game of random chance, a cosmic pinball machine. For it to begin a runaway reaction, it would need to just happen to collide directly with a nucleus, an event of incredibly low probability, especially for a microscopic particle. Even if it did, a single conversion would release a tremendous amount of energy, potentially blasting the strangelet away and disrupting the surrounding material, preventing it from finding its next victim. A neutral strangelet is a clumsy assassin, not an efficient catalyst for planetary doom. This leaves only one truly terrifying possibility, a strangelet with a large times negative times charge. This is the monster of our nightmares. Such a particle would be a perfect predator. The positive fortress of the atomic nucleus would become a beacon, an irresistible lure. The negatively charged strangelet would be actively, powerfully drawn toward it, accelerating across the atomic void. The electrostatic barrier that protected the nucleus from a positive strangelet would now become a welcome mat, pulling the agent of conversion inward. Once it made contact, the strong force would take over, the quarks would be rearranged, and the nucleus would be consumed, its mass and charge added to the growing strangelet, making it an even more effective and attractive predator for the next nucleus. This is the only scenario that could plausibly lead to a runaway chain reaction. This is the Ice-9 particle. So the billion-dollar question becomes, how likely is it that a strangelet formed in a collider would be negatively charged? The answer once again is found in the refined details of physics. Strangelets are born from a soup of quarks and gluons, a plasma where charges are balanced. The initial state of any forming strangelet is expected to be either neutral or slightly positive, simply due to the masses and charges of its constituent up, down, and strange quarks. To become the negatively charged monster, it would need to actively capture and hold onto electrons from its environment. This is no simple task. The strangelet itself is a fantastically dense object. For an electron to be captured, it must overcome its own quantum repulsion and find a stable energy state within the strangelet's structure. The conditions required for this to happen are extreme, and most importantly, they take time. The fireball created in a particle accelerator like the Large Hadron Collider exists for less than a yoctosecond, a septillionth of a second. It expands and cools at nearly the speed of light. There is simply no time for a nascent strangelet to cool down, stabilize, and begin scavenging for electrons to build up its negative charge. It's like trying to build a sandcastle in the middle of a thermonuclear blast. The environment is too chaotic, the timescale too brief. By the time the scene has cooled enough for such a process to even begin, the particles created in the collision are already gone, flying at relativistic speeds into heavily shielded beam dumps. The window of opportunity for creating the doomsday particle slams shut almost at the very instant it opens. The charge barrier holds. The second gate remains secure. Even if we dismiss the arguments from theoretical physics, if we believe that both the stability window and the negative charge problem can somehow be overcome, there is a third and final line of defense. It is not a theoretical calculation or a computer simulation. It is an observation, an experiment that has already been run for us on a colossal scale over a period of billions of years. We need only look up at the night sky. Our universe is bathed in a constant shower of cosmic rays, particles, mostly protons, and atomic nuclei, accelerated to incredible energies by supernovas and black holes. These cosmic rays are nature's own particle accelerators, and they are far more powerful than anything we could ever hope to build on Earth. The most energetic cosmic rays strike our upper atmosphere with the kinetic energy of a major league fastball, all concentrated into a single subatomic particle. For 4.5 billion years, these cosmic bullets have been relentlessly bombarding every object in our solar system. Consider the Moon. It has no thick atmosphere to protect it, no magnetic field to deflect these particles. Its surface is an ancient, pristine ledger of cosmic impacts. Over the eons, the lunar regolith has been subjected to a number of high-energy particle collisions that dwarfs the total number of collisions in all of our particle accelerators combined by many, many orders of magnitude. The energies involved are also often far higher. If the creation of stable, dangerous strangelets were a likely outcome of such high-energy collisions, we would expect to see the consequences. The Moon would be the ultimate strangelet detector. A single dangerous strangelet created on its surface would have had billions of years to convert our celestial companion into a 3,500 kilometer wide sphere of strange matter. Yet when we look at the Moon, we see rock. We have sent astronauts to its surface. They have walked on it, collected samples, and brought them home. Those samples are made of silicon, oxygen, aluminum, and iron, perfectly ordinary matter. The cosmic jury has returned its verdict. Billions of years of the universe's most violent collisions occurring constantly right on our cosmic doorstep have failed to produce a single world-ending particle. The galaxy-scale experiment has been performed, and its result is null. This is perhaps the single most powerful piece of evidence we have that the Strangelet doomsday scenario is not a realistic threat. The universe has already tried and failed to make it happen. We can take this cosmic argument one step further into the most extreme environments imaginable, the hearts of neutron stars. As we've seen, these stellar remnants are the most likely places in the cosmos to find strange matter. They are gigantic spheres of densely packed nuclear matter, crushed under a gravitational vice so intense that atoms have ceased to exist. They are in effect naturally occurring laboratories for high-density physics. Many theories suggest that the immense pressure at the core of a massive neutron star should be enough to squeeze neutrons and protons into their constituent quarks, forming a stable core of strange quark matter. If the Bodmer-Witten hypothesis is true, and this conversion process were easy and exothermic, we would expect that any neutron star massive enough to begin this process would undergo a runaway conversion. The entire star would rapidly transform into a strange star. Such a conversion would release a staggering burst of energy, a cosmic firework visible across the galaxy. While strange stars are theoretically plausible, and astronomers search for them, our observations of neutron stars are largely consistent with them being made of neutron matter. We see them cooling at predictable rates, we measure their masses and radii, and we observe their magnetic fields. While some data points remain puzzling, there is no definitive evidence of a widespread population of strange stars. If the conversion were an easy, unstoppable process, we might expect most times old massive neutron stars to have already made the transition. The fact that we see a universe full of seemingly normal neutron stars suggests that the conversion process is either not favored by nature, is incredibly slow, or only happens under conditions even more extreme than those found in a typical neutron star core. The cosmic laboratories themselves seem to be telling us that the chain reaction is not the default outcome. So we bring this cosmic perspective back to Earth, back to the polished chrome tunnels of the Large Hadron Collider. Here, scientists are not trying to create doomsday particles. They are trying to recreate for the briefest of moments the conditions of the primordial universe. They smash together heavy ions like gold or lead to create a fleeting fireball of quark-gluon plasma. The goal is to study this exotic state of matter to understand the fundamental force that holds our universe together. The energies are immense by human standards, but they are dwarfed by the cosmic rays that strike the moon every second. The time frame is infinitesimal. The created plasma, a microscopic droplet that exists only for the time it takes light to cross a few atomic nuclei before it expands, cools, and freezes back into the ordinary protons and neutrons we know. The safety analyses for these experiments are the most rigorous in the history of science, reviewed by independent panels of physicists considering every single one of these arguments. They conclude with overwhelming confidence that the conditions created are simply wrong for the Ice-9 scenario. There isn't enough time to form a stable multi-quark strangelet. There isn't a viable mechanism for it to acquire the large negative charge it would need to be dangerous. And even on the impossible chance that a microscopic neutral strangelet were formed, it would be travelling at over 99.9%, the speed of light, instantly vanishing into a block of graphite and steel a kilometre away, with no opportunity to ever interact with the planet beneath it. The machine designed to probe the universe's deepest secrets has also been designed with its most profound safeguards. The journey into the heart of strange matter has led us here to a place not of terror, but of deep reassurance. The monster we envisioned, the ultimate grey goo, is caged by the very laws of physics that allowed us to conceive of it. Its stability is a quantum longshot. Its predatory nature is neutralized by the fundamental forces of electricity, and its existence is contradicted by billions of years of cosmic history written across the face of our own moon. The threat, while fascinating to contemplate, recedes from the world of plausible risk and into the realm of profound science fiction. The fear was born from a sliver of possibility in our equations, but it is vanquished by the vast interlocking architecture of physical law and astronomical observation. But this does not make strange matter any less compelling. In fact, it is the opposite. Freed from the shadow of apocalypse, we can now see it for what it truly is, a tantalizing clue to the ultimate nature of reality. It remains a deep and beautiful puzzle. Does it exist in the crushing heart of neutron stars, a hidden state of matter in the universe's most extreme crucibles? What can its theoretical properties tell us about the strong nuclear force, the glue that binds the cosmos? The quest To understand strange matter is not about preventing the end of the world. It is about completing our map of it, about understanding the full range of possibilities that matter can explore, from the familiar world around us to the alien landscapes that lie hidden inside the collapsed cores of suns. The story of the Strangelet is not a horror story after all. It is a story of our own growing wisdom, of our ability to confront the deepest questions and find our answers not in fear but in the magnificent self-regulating logic of the cosmos itself. And so, we arrive at the end of our journey, standing at the precipice of a fear that once threatened to consume the very ambition of modern physics. We have travelled from the pristine, almost mathematical elegance of the Quark model, a theory born in the minds of geniuses trying to impose order on a chaotic subatomic zoo. We saw how this elegant theory contained a ghost, a strange and unsettling possibility, a loophole in the laws of stability. We gave it a name, strange matter. You have followed this idea as it crawled from the chalkboards of theorists and took on a terrifying life of its own. It was no longer just an equation. It became a story, a dark fairy tale of physics, where the universe's most stable substance was also its most voracious predator. We imagined it together, this hypothetical seed of ultimate truth, the Strangelet, an object so perfectly bound, so energetically favourable, that it would represent the ground state of all existence. Next to it, the matter that constitutes you, me, and everything we have ever known would be a mere house of cards, a temporary arrangement, waiting for the slightest touch from this cosmic anchor. The terror of this concept, as we have explored, lay in its quiet, inexorable logic. It was not a bomb which explodes with sound and fury. It was a catalyst, a conversion. The Ice Nine scenario, a fictional horror story, suddenly found a plausible, chilling analogue in the heart of particle physics. A single microscopic strangelet touching a single atom could theoretically initiate a runaway chain reaction, a silent, unstoppable wave of transformation that would not shatter our world, but rewrite it into a new, bizarre form of matter, leaving behind a dense, smouldering sphere of strangeness where our vibrant planet once orbited the Sunday. This was the fear that escaped the laboratory. It seeped into the public consciousness, fueled by headlines and the innate human anxiety of unleashing a power we cannot control. The story of strange matter became a cautionary tale for the 21st century. It pitted the relentless pursuit of knowledge against the primal instinct for survival. This epic narrative reached its fever pitch with the advent of humanity's most powerful scientific instruments, the Great Particle Colliders. At the relativistic Heavy Ion Collider and later at the Large Hadron Collider, we set out to do something extraordinary. We sought to recreate the universe as it was in its first microsecond of existence. We aimed to build a time machine, not of gears and dials, but of pure energy designed to melt the very protons and neutrons that form the bedrock of our reality. The goal was to liberate quarks and gluons, to witness for a fleeting instant the quark-gluon plasma, the primordial soup from which everything emerged. Yet within that magnificent scientific ambition, the old fear stirred. What if in that momentary inferno we accidentally forged the seed of our own destruction? What if our quest to understand the beginning inadvertently created the end? This was no longer a philosophical debate. It was a tangible question, a risk assessment on a planetary scale. The controversy became a crucible, a trial by fire for the entire scientific enterprise. It forced a profound and necessary confrontation between the creators of knowledge and the society they serve. The public's alarm, far from being a nuisance, was a legitimate expression of the stakes involved. When scientists speak of reordering the fundamental nature of matter, humanity has a right to a duty to ask, are you sure? Are you absolutely certain you know what you are doing? The questions were sharp, the accusations pointed, and the potential consequences were literally unimaginable. In this crucible, science did not retreat into an ivory tower. It responded, it engaged, it subjected its own ambitions to the most intense and rigorous scrutiny imaginable. Safety committees were formed, populated by independent physicists, Nobel laureates, and experts from every related field. They were tasked with an unprecedented responsibility to play devil's advocate against their own colleagues, to search for any plausible pathway to catastrophe, and to do so with the weight of the world on their shoulders. they did not dismiss the concerns. They honored them with the full power of the scientific method. They painstakingly reviewed every calculation, every assumption, every piece of data. They treated the Ice-9 scenario not as science fiction, but as a serious hypothesis that required a definitive evidence-based refutation. What emerged from this period of intense self-examination was one of the most elegant and reassuring arguments in the history of science, a multi-layered defense against our deepest fears. The first line of that defense was written not in our laboratories, but in the heavens. We realized that we were not the first to conduct these experiments. Nature, in its boundless creative and destructive power, has been running a far more ambitious version of the Large Hadron Collider for billions of years. Cosmic rays particles accelerated to energies millions of times greater than anything we can achieve on Earth have been bombarding our planet and every other celestial body in the solar system since time immemorial. They have slammed into our atmosphere, into the moon, into the planets, creating countless microscopic fireballs of extreme energy. The moon in particular became our silent, steadfast witness. It has no protective magnetic field, no thick atmosphere. For 4.5 billion years, it has been an unwavering target, absorbing a relentless barrage of cosmic energy. If the creation of stable, planet-devouring strangelets were a likely outcome of such high-energy collisions, the moon would have been converted into a sphere of strange matter eons ago. Its continued existence, its silent, rocky face gazing back at us, is perhaps the most powerful piece of experimental evidence we could ever hope for. The universe, it turns out, had already run the safety trial for us. We were simply late to read the results. But the inquiry didn't stop there. The scientific community pushed deeper, turning its gaze to the most extreme environments in the known cosmos, the cores of neutron stars. These incredible objects, the collapsed remnants of massive stars, are the universe's own pressure cookers. They are city-sized spheres, where matter is crushed to densities so immense that a single teaspoon would outweigh a mountain. Here, in these gravitational furnaces, the conditions are far more favorable for the formation of strange matter than in any collider on Earth. For decades, physicists have theorized that the immense pressure at the heart of a neutron star should inevitably squeeze protons and neutrons so tightly that their constituent quarks would reconfigure themselves into the more stable, strange matter. Some predicted that many or even all neutron stars should actually be strange stars, their interiors composed entirely of this exotic substance. Yet as our observations have grown more sophisticated, as we have learned to interpret the subtle signals of light, gravity and radiation from these distant cosmic gyroscopes, a different picture has emerged. We have measured their mass, their radius, their cooling rates and their behavior in binary systems, and the data consistently suggests that most neutron stars are just that, stars made of neutrons. They do not seem to possess the properties predicted for strange stars. This profound cosmic clue tells us something vital. It suggests that the conversion to strange matter is not an easy automatic process. It implies that there is a significant energy barrier, a hurdle that is difficult to overcome even in the most extreme natural environments. The creation of a stable strangelet, it seems, is a far more delicate and unlikely event than the early fearful models suggested. The universe's most powerful laboratories, the hearts of dead stars, whisper a story not of inevitable conversion, but of profound resilience in the matter we call normal. The monster at the heart of the atom was, it appeared, far more reluctant to be born than we had ever imagined. And so the fear began to recede, replaced not by complacency but by a more nuanced and profound understanding. The story of strange matter was transformed. It was no longer a simple tale of hubris and potential doom. It became a testament to the self-correcting, evidence-based power of scientific inquiry. The entire episode forced a new level of maturity in the relationship between frontier science and the public, establishing a new precedent for transparency and rigorous independent safety verification. We learned that our greatest tools of discovery must be accompanied by our deepest sense of responsibility. The process worked. The questions were asked, the evidence was gathered, the arguments were tested, and a consensus was reached grounded in the observable reality of the cosmos itself. We had stared into the abyss, and the abyss had shown us that the laws of physics, while full of wonders, also possessed a deep and reassuring stability. With the spectre of planetary annihilation laid to rest, the search for strange matter continues today, but its character has fundamentally changed. It is no longer a search for a hidden threat. It is a quest for a key, a Rosetta Stone, that could help us decipher the universe's most esoteric secrets. The possibility of its existence, however remote, has become a powerful diagnostic tool. Physicists now hunt for signs of it, not with trepidation, but with the excitement of explorers entering an uncharted wilderness. If we could detect a strangelet perhaps arriving as a cosmic ray, or identify the signature of a strange star, it would revolutionize our understanding of the fundamental forces. It would confirm a crucial, untested prediction of the Standard Model and provide the first concrete evidence of a world beyond protons and neutrons. It would give us a physical sample of the kind of matter that likely exists in the crushing abyss of neutron star cores, allowing us to test theories of extreme density that are currently confined to supercomputers. The search pushes us to refine our detectors, to devise new ways of sifting through the constant rain of cosmic particles, looking for that one anomalous track, that one impossibly heavy charged neutral candidate that could be the herald of a new physics. The dream is to find a piece of the cosmic core here on Earth. Furthermore, the physics of strange matter provides a unique window back into the birth of the universe. In the first microseconds after the Big Bang, the cosmos was filled with the quark gluon plasma we struggle to recreate in our colliders. As the universe expanded and cooled, this primordial soup condensed into the particles we know today. But could some pockets, some tiny droplets of the quark gluon plasma containing strange quarks, have survived this violent transition? Could ancient strangelets forged in the crucible of creation itself still be drifting through the cosmos today, relics of our universe's birth? Finding one would be like finding a fossil from the first moment of time. It would be a direct physical link to the origin of all things. This, then, is the modern legacy of strange matter. It is a concept that forced us to confront our deepest fears about our own power, and in doing so taught us invaluable lessons about scientific responsibility and the unyielding logic of the cosmos. It has evolved from a doomsday scenario into a subtle, powerful probe of nature's extremes. It continues to challenge our assumptions, pushing theorists to refine their models of quantum chromodynamics and inspiring experimentalists to build ever more sensitive instruments. It reminds us that the universe is under no obligation to be simple, and that the forms of matter permitted by its laws may be far more varied and exotic than what we experience in our everyday lives. The quest remains one of the great unfinished chapters in physics, a tantalizing puzzle that connects the inner world of the quark to the outer limits of cosmology. We began this story with a question of survival, a fear born from a strange new idea. We end it with a testament to the enduring power of human curiosity. The journey of strange matter mirrors our own intellectual evolution. We venture into the unknown, and what we initially perceive as a monster is often, upon closer inspection, a guide to a deeper and more wondrous reality. The word strange in physics is not a judgment, it is an invitation. It is a label we attach to phenomena that defy our current understanding, signaling a frontier where the next great discoveries lie waiting. The search for strange matter is in its essence a search for ourselves, for the ultimate rules that govern our existence, from the smallest constituent of our atoms to the grand, sweeping arc of cosmic history. It is a reminder that in science, the most unsettling questions often lead to the most profound answers, and that our willingness to explore even the most strange of ideas is the engine that drives us forward forever, pushing the boundaries of what it means to know.